All right, Avenue code, day 12. What do we got? Number of arrangements for each row. Sum. See. Oh, it's polyominoes. Okay. Nonograms, that's the name. Sure. 5 copies. Okay. 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 So what is the state here? 1, not 1. Okay, that does actually give 21. Cool. Okay. Interesting problem today. So what's going on? So we are given this input with a bunch of question marks, and we're supposed to fill it out as, count the number of ways we can fill it out as a nonograms line, which is a logic puzzle, kind of like Sudoku. So for example, this one is saying there's a block of 1 hash mark, there's another block of 1 hash mark with some dots between the blocks, and there's a block of 3 hash marks. Well, here's the block of 3 hash marks. And then these 3 must be 2 blocks of 1, so they must be hash mark dot hash mark. Right. This one has 1 block of 1 with some spaces, then another block of 1, and 3. This must be the 3, but either of these could be the 1, and either of these could be the 1, so there's 4 here, and so on. So that's part 1. And so I solved this using brute force for part 1 and dynamic programming for part 2. So let me, I guess, explain what I mean. I guess I deleted my brute force, but so I mean, this is basically brute force if you take out the DP table. Okay, sorry. So what do I mean? So first we go through all of the lines. So this is just parsing, right? We split it into like some stuff we need to fill out and the numbers. This is part 2 stuff. We grab the actual list of numbers. We compute the answer for this line. We add that to our answer, and we print out the final answer. Okay, so how do we actually compute it for a line? So we have the 2 pieces of input, the sort of template that we have to follow with question marks, dots, and hash marks, the lengths that we're looking for, and then so these are never going to change, and then this is our current sort of state. So what character we're looking at, which block we're trying to fill out currently, and how long our current block of hashes is, which turns out to be enough to keep track of where we are. Dots, bi, current position within blocks, and current equals length of current block of hash marks. And so the point is, if we keep track of this, we don't need to remember exactly how we filled in everything so far, which will be important for part 2. And I don't know, it should be somewhat clear that this is enough sort of information. So let's see how we use it. So ignore the stuff about DP for now. So if we're done, right, that is, if we're sort of past the last character, we filled in everything. So there's 2 good cases. We could be done with all the blocks and not have a current set of hashes going on. That's valid. Or we could be on the last block and have it completely filled in. That's also valid. And otherwise, it's no good, right? Either we had some stuff like left over, or I don't know, too much stuff or something, right? Or we have like a block of the wrong length. This is no good. Okay, if we're not at the end, then we can consider putting a dot here, and we can consider putting a hash mark here. So if it's a question mark, we can put either one. Otherwise, we can only put whatever character we already have. And then, so what are the cases in which putting a dot is okay? If you had previously had a dot, right, you don't have anything going on right now, then okay, fine. We just move to the next character, we're still on the same block, and we still have a length of 0. This is the most interesting case, where we are ending a block. So we currently have a block, and we actually have a block that we expect to see, and it's the right length. Then we can say, okay, move on to the next character, and also move on to the next block, and also we currently have a length of 0. And if we put down a hash mark, that just increments the length of our current block, possibly from 0 to 1. But it doesn't like end the block, and it moves us on to the next character. So that is really it, and that will work fine for part 1. In fact, let me just modify this to do both. So if we don't use the DP table at all, that will solve part 1 pretty quickly, but that will take ages to solve part 2. Like, look at how big this number is. And hopefully I didn't break anything. Indeed, the answer was 7857. Okay. But you can see it's running forever. This function was used for the brute force, but it's not really used any longer. So now let's turn on the DP table. And we can see that it fairly quickly computes this very large number. So how does that work? So I mentioned that this is sufficient state to keep track of what's going on. Right? The sort of more natural thing to do, and the thing I did in my brute force, is just to like fill in characters as you go, and then at the end see if the characters you filled in match the set of blocks that you expected. But this is no good for part 2 because it doesn't let you. The state space is too big. Because you're remembering too much information about what's happened so far. So this is like the minimal amount of information that you need to remember, and this lets you collapse a bunch of states together. So let me go back maybe to this example. So once we've filled in, one of these we know needs to be a hash mark, but once we're like here, we don't really care which one ended up being the hash mark. We just need to know that we fulfilled this block. And similarly, once we're here, we don't need to know, which of the 4 possibilities we had. We just know that we filled in these 2 blocks. So that's the idea behind the dynamic programming solution. Is you instead of keeping track of exactly what you've done so far, you just keep track of what you need to know if this is going to be successful. And the point is that this state space is relatively small. Len dots times len blocks times, sure, current is less than or equal to len blocks, or len dots, that's true. And that is not valid Python. Like, how big does our table get? I don't know. Not that big, I guess, is the point. So the point of dynamic programming is to reuse answers that you already computed, right? If you just brute force this, then the running time is 2 to the number of question marks, which is a lot. But if we've already seen this situation before, we don't need to recompute what the answer is. We can just store whatever the answer was in this table, and then if we see it again, we can just look up that answer and use it. And that is a huge runtime savings. It gets us down from like 2 to the len of dots to len dots squared times blocks, basically. Which, yeah, big savings. And they're just, so this is the point of, I guess, being careful about defining the state, is there's just not that many different situations going on, right? Because all we really care about is like which blocks we've consumed and how far we are into the current block, which is just not that, there's not that many possibilities for that. Right, so there's like two effects going on here. One that's actually less important is that we're sort of early stopping. Like if you put hash hash, actually that's not even true. But if you put hash hash, we could stop early. That's never going to work because we have a 2 and we're expecting a 1. But the more important thing is just that is this like reusing of situations that we've seen before, and there just aren't that many possible situations, even though sort of the, I don't know, the game tree or something, like, you know, sort of if you tried all the possibilities, there's 2 to the number of question marks, but many of those possibilities sort of merge with each other. There aren't that many distinct situations. You know, because all we care about is like how the question marks sort of fill in the expected blocks, and there just aren't that many ways to do that. Yeah, so hopefully that made some sense. Cool problem. I don't think there's a way to do this without dynamic programming, but maybe someone will prove me wrong. Anyway, that's it for day 12. See you tomorrow.